So, gives me great pleasure to welcome Jacob Abernethy. So Jake was mentioning he has been to Cornell before, but he has not been to ORIE. So this introduction was supposed to be given by David Schmoes, who's not here, so I'm sort of stepping in. And the reason I'm mentioning it is I usually, before I do the introduction, I hope that the abstract will have enough in the bio which lets me say certain things. But if you look at Jake's abstract, you'll basically see that he's saying he's from Georgia Tech and works on learning theory and pretty much nothing else, which is either a sign that he wants me to sort of stop fast or he wants me to make up something interesting about it. Given this is a talk about playing games, I'm going to assume he wants me to make up things about it. So, okay, so interesting facts about Jake. As many of you would have realized if you're on his schedule, and as I realized when I tried inviting him, Jake's official email is prof@gatech.edu. And I can make up stories about how this is very representative of his research, how he sort of always finds like the simplest way of thinking about things, etc., etc. But I think I'll just leave it out there. prof@georgiatech.edu. So that's fact number one. Fact number two, I think many of us, or at least I know Jake's work very well, as he's done some amazingly foundational work in like thinking about online learning and the connections between online learning and games. In particular, especially for an OR audience, if any of you have not read how Blackwell approachability and no-regret learning are equivalent, this is one of my favorite papers of all time. So if you get bored during the talk, feel free to go and read that paper. But on the other hand, for many of us, and this was new to me, even though I think of Jake as mostly doing foundational theoretical work, he actually uses learning for real things. So he has a line of work on finding lead pipes in Flint, Michigan using machine learning. And the first time I was told this, I was actually really surprised. And I kind of for a while thought maybe there's someone else called Jake Abernethy, but if you go to the paper, it says, well, the email address is prof@georgiatech.edu, so had to be him. I think that's all I can make up about him. So
thank you.
Over to Jake.
Thanks for that intro. I'm flattered, and I didn't know you know all of my most boring papers. So I'm actually, it was funny. I actually was thinking about this talk today, and I said I was going to give a talk on one topic, but actually I thought more about it and decided I should actually give a very short mini talk first. And this is going to be like, so I have this what you see here is a theoretical talk. I have another talk that I made a very short version of it. That is just, I think I want to kind of start with this. I think hopefully people at home can see the different, this different thing. This is really going to be like completely applied. This is an OR department, and this is like a very kind of cool application of kind of what is like real world OR. Now, I mean, I'm a theoretical computer scientist. Like nothing that I do ever even gets implemented anywhere, even in some downstream way. So suddenly I found myself in this project with this like finding lead pipes that somehow like my work is actually being used directly across now dozens of cities. So let me just talk briefly about this. I think it's a cool discussion, and it'll let me this will be interesting to a broad audience. And I'm going to try to wrap it up in a few minutes. So I'll just mention that in 2016 there was this big problem after the Flint water crisis where they had over $100 million to find the city's lead pipes and replace them. And this gentleman was put in charge of that project. We met him and started talking to him. How did it all start is that So the problem with lead pipes and finding lead pipes is that unfortunately when people bury these pipes underground, and these are particular pipes, ones that connect homes to a water system, when they install these pipes, they didn't necessarily write down what they were. And if they did write them down, they probably were wrong or they were changed at some point. These are like the records they had in Flint, Michigan. At the time when we started this in 2016, we actually were literally peeling through these books of water damage records. At the time, I had this data science team that I'd been working with at the University of Michigan. And so we just treated this like a Kaggle problem. Oh, can we just predict which homes have lead pipes, which ones don't? And we actually had a small amount of data at the time. This is how it all kind of got started. And we really just treated it like a simple basic prediction problem. Can we get a probability estimate that this particular home has a lead pipe using known information about the home? How old is it? How big is it? How valuable is it? How far is it from the street? How many stories is it? Census information, any water sampling information we have about it, how much water usage they've had, all these different variables. Can you predict whether this home would have a lead pipe? And it's actually a surprisingly easy problem. I mean, when I say easy, you can get pretty high accuracy just using basic profile information about a house. Okay, so where did this go? The key challenge with this type of problem is that gathering data is absurdly expensive. If you go and you show up to a home and you dig a massive hole in the street to replace a pipe, and you find copper pipes, you've just wasted $6,000. And it could be more. I mean, it depends on the type of infrastructure they have. You may hit a gas line along the way trying to replace a pipe. So $6,000. And so, when we first came with, they said, oh, well, every time we make a mistake, we pay $6,000. We asked them, well, do you have a way to more cheaply find out if a home has a lead or a copper pipe before you go and do this? And they said, yeah, there actually is a way using this cheaper digging process. We can kind of dig a small hole first and then just try to look in with a camera or something. And and one of the ways that we really influenced this process by saying, can we do this data gathering for you? Can we manage the next data gathering? And we literally were sending spreadsheets back and forth to the city to city officials to do these inspections, gather actual labels. We needed labels for this problem. And I should just mention that there could be multiple segments of pipe underground, so you actually have to look at all of them. So anyway, I mean, our performance in this project was decent. You can see that when you see a red dot, it means that a crew was sent to this is in February, this is later on in 2017 in October. When you send a crew to do a replacement, do they find a lead pipe or not? You want them, and it seems bad, but you want them to find a lead pipe so they don't waste the money on the replacement. And green dot means we sort of made a mistake. And there were certain neighborhoods that weren't as good as others, but our performance at the end of October, at the end of 2017, was around 85%. So they were finding lead pipes at most places that they went to. This is a plot of the hit rate of our kind of recommended homes over time. We had some bad months, but again, there wasn't a lot of replacements being done here. A lot more were done in this period. This is the hit rate performance of our methods at the time. And then what's kind of interesting about this is that the city of Flint decided to hire a much larger engineering firm, and they gave them a $5 million contract. We were getting paid. We were not getting paid anything. We were just doing this pro bono. They brought in this large engineering firm, and they didn't listen to us. They sort of didn't respond to our emails and said, oh, we have this model. We're doing this machine learning. It's cool, and you should use it at least. And they just didn't address that. So journalists kind of picked up the story, and we're noticing that the rate of replacement had gone down dramatically, despite the fact that the number of attempted replacements was still very high. And there's this big Atlantic article that came out after they spoke to us, and the title was "How a Feel-Good AI Story Went Wrong in Flint." So we were part of this interesting news narrative that somehow large contracting firms weren't really focusing on the problem at hand, which is actually finding and replacing the pipes. So I'll just mention that this was eventually resolved in. Oh, sorry. So just so you can see what was the performance over time. This is when we were involved. This is when the engineering consulting firm was involved. That went from 85% to about 15%. 15%. That's how often they were finding lead pipes when they tried to do a replacement. So they were just wasting, $4,000, $5,000 every, more than 3/4 of the time. Okay, so it turns out this whole thing was resolved in the courts. We actually submitted affidavits and stuff, and eventually, the federal court said every single home that receives a replacement in Flint will be directed by these two professors. It was me and my friend Eric Schwartz, my collaborator on this. So suddenly I was in charge of $30 million of spending, which was very scary. I write math papers. I'm not used to having to decide how government funding is spent. But this is the NRDC, the National Resource Defense Council, basically used this as a sort of a neutral third party to kind of help make this program more efficient. And we would send spreadsheets back and forth to the city where we thought they should be spending the resources, and it was a sort of a nerve-wracking period because we knew that we were suddenly responsible for something which was very important and was going to be was very costly. So anyway, you can see this is the performance of the program as after we were put back in charge. So and this plot, I should just say, the cool thing about this story, the reason why I love telling it, even though it has nothing to do with my more mathematically focused research, this plot turned into a company. And that company is called Blue Conduit, and it was co-founded in 2019. What happened was, as soon as the story came out about the work we'd done, other cities were saying, oh, we have this problem too. At the time, it wasn't clear how many cities have this problem. There's a lot of cities across the U.S. any city that was basically that grew between 1880 and 1950, had large growth then, and maybe not a lot of growth after, there's lead pipes in the ground, for sure. There's probably a lot. It could be more than half of the town. So a lot of towns just aren't addressing it. And so now there's been an interesting change in the last 6 months. There's a lot more interest in this problem. But we sort of, we picked the right timing on this. You'll notice now there's been all this political focus on replacing lead pipes, and suddenly the federal government has decided that they're going to invest. Right now there's $15 billion in the current infrastructure bill, which is passed. They're discussing another $30 billion in spending in the Build Back Better plan. So it was a good timing, and I'll just mention that there's been a lot of attention. I was just saying on my way here. So the reason I'm doing this talk now is on my way here in the airport, I stopped at the newsstand and I saw this Time Best Inventions of 2021, and Blue Conduit is here on page I don't know, somewhere over here. So we've been getting a lot of attention recently. Anyway, I'll let anyone who wants to look at that take a look at. I literally picked it up in the airport this week. So I guess I'll stop there, and if there are any questions about that project, I'm going to put that aside for now and just say this is a cool kind of side thing that I've been doing recently. Any questions about replacing lead pipes? Yeah.
Well, when you're designing the algorithm for Detroit, I'm wondering how much of that just translates directly over to a different city, and how much of it has to be sort of retrained.
Yeah, I mean it does.
Get the real data.
It does need to be. So we kind of treat cities. Every city we go to, we're not going to make any assumptions. We're not going to assume that the model just somehow immediately transfers. We sort of say, look, you need to do some inspections. We need to gather 200 data points first. And that, by the way, is an expensive process. Even if $300 for a hole times 200, that's already $60,000. So that's actually the hardest sales pitch to cities. Is like, we kind of need you to do this data gathering first. And they're like, ooh, that's a lot of money for us to spend off the bat before we get anything from. We can't give them anything until they do this. So we try to sort of start from scratch. We don't actually have enough data yet to really try and see if some transfer learning would be helpful. We're actually not there yet, but that doesn't mean that we're presumably some of the value that Blue Conduit can provide is say, we have so much experience in other cities, but literally we have a model from other cities that should be applicable to your city even in advance. But again, we're kind of still in the early days of that, but it's a good question.
Are there cool experimental design questions? I would think that if one house has, this water main has lead, it's made out of lead, then the one next to it.
Yeah. Spatial modeling is a big part of the model. So yeah, we're definitely doing a lot of spatial modeling stuff, and in fact, it's very important for the operationalizing of this because they tend to close off a block. So if, what was happening in this the Flint story was that they were when this other firm had come in, they were telling a crew just go to the whole block. But if you find copper at one home, you find copper at the next home. If I cover the home, you should stop at that point and then go to another neighborhood. And they were just saying, no, just keep going, because we had to get these homes done. And you really don't want to do that. I mean, you can come back and maybe do an inspection at the next home later on, but you're wasting time in this neighborhood now. You need to go in. Does anyone have a question at home?
Yeah, I have a question. Can you just test the water? I mean, it's a good question. Can you test the water? Yeah. So it turns out that you can test the water. The water tests are slightly predictive, but they're very weakly predictive. And there's a reason for this. We actually looked at turns out Flint, they have a ton of water testing data. I mean, they literally have tens of thousands of samples of water testing data across the city. It is surprising how uncorrelated the water tests are to the presence of a lead pipe. And that might seem strange. And it turns out the reason for this is that when you test water for lead, you have no idea where the lead came from. People can have lead fixtures in their home, and those things often can flake lead. You can have lead solder somewhere. And we've noticed that there is a correlation between having lead pipe and having lead in your water, but it is actually much less predictive than, for example, knowing the age of the property. If you know the age of the property, you get a lot more information about the likelihood of a lead pipe than a water test. The water tests are just so noisy that they're not actually as helpful as you might expect. So I'm wondering, if you could track where the water is going, presumably it's coming from, the water source to the home, and is there a sort of, dependence between, there are, 5 lead pipes that this water had to cross, and
Okay, so
fire.
I think if I answer the question, I'm going to answer this question. It's a good question. The key thing is that lead pipes are only used for small pipes. You would never use a lead pipe for a water main. They're too large. Lead pipes are for like snaking through yards. So you kind of want to go around a root. That's why they would use lead, because it's nice and soft. You can kind of like bend it around a tree. And so the only time you're actually going to have a lead pipe is at the property line, or at least under the street. The water mains are too large for using lead. So if it picked up lead somewhere, it picked it up from either the service line or from somewhere in the home. It's definitely not coming from this. The source is clean water. I mean, they can test that and be very careful with the source of the water. If it's going to pick up lead, it's picking it up somewhere, under the street or in the home.
Gotcha. Thank you.
That's my understanding, at least. Any final questions about? Yeah.
Do you find that the information you collect across cities varies much? And if so, I mean, in the data points.
It does. It does vary a lot. It's pretty variable. Yeah. Different cities had different policies for how they were installing these things. Sometimes it was done by private contractors. Sometimes city government. So there's clearly a lot of heterogeneity of how the water infrastructure was built at the time.
So how do you determine like what kind of information to look for when you say survey another city?
I mean, from the naive perspective, what we need is just the tax parcel information that describes the homes, and we need to get some labels for which homes have these lead pipes and which ones don't. And that's basically the kind of core thing. We get more information too, and we often ask cities if they have other data, census data, demographic data. And there's other things that can be useful, but those are the kind of core things that we need. And it's surprising, a lot of the work that we do is just like figuring out who the person in the city that has the data that can download a CSV, and that actually is surprisingly hard to do when you work with the city. Most of what we do is very low tech. I mean, it's hard to get it into the point where you actually you can use an algorithm. Yeah.
Is this data public?
Not typically. Some states it is. Some states publicize their information about all their parcels. They have, like, New York City has a great open data portal, but most towns do not publicize the data. Yeah.
Is it logistic regression or something fancy?
I mean, yeah. Is my whole company, does it boil down to XGBoost? And the answer is 95% of the way, yes, it does actually boil down to using XGBoost at the right location. Yes, then the machine learning is actually not, I mean, there is some spatial modeling, there's some other things, but you can get a lot of the way with some basic machine learning algorithms. Most of the things that we do is not the interesting data science. I hate to admit this, I hate to say this to a bunch of academics, but most of what we do is just setting up the infrastructure to help the city even try to apply an algorithm. And they understand, it's probably some way to make this more efficient, and but we just have to get their data in our system and then make it visible and usable for them. And that really is a huge part of what we do. The kind of machine learning part is sort of, the interesting parts are kind of pretty small in terms of the labor, our own, company labor. Hopefully in the future, it'll be easy to insert a Ph.D. into a problem. But I'm just, my experience with this is that it's very hard to get the skills of someone who has a Ph.D. in, let's say, operations into an organization and have them be productive immediately. There's so many barriers between just getting, you guys being useful. And I think these startup companies like ours are helping this a little bit, but there's like a lot of distance between what cities do and what we do here in operations research departments.
Your experience is what I typically.
Yeah, I think a lot of faculty have tried doing consulting for organizations. They find the same thing. Okay, one last question. Okay, let's do the math now. I'm excited about this other topic, and I have to say I made new slides for this. Can everyone at home see the new building algorithm by playing games?
Looks great.
Good. Okay, so what I'm going to talk about today is a kind of a sequence of research papers that have been working on for the last 5 years. Actually, sort of around the time I started with the Flint and this, and we're about 5-year-old projects. Okay, and I just finished a journal version. I just submitted a journal version with my student Junkun Wong and Kafir Levy on this topic. And so I actually decided to rewrite my entire talk last night to be a little bit more we really summarized a lot of this work. Let me give you a high-level view of what this area is about. So I want to emphasize something. now when people think about machine learning, if you look at applications of machine learning, somehow games are all over the place. Now, people playing games, using it for video games or game solvers, solving chess, multi-agent systems. You just hear games everywhere. People, competitive environments. I just say, when I started grad school, if you told me that was a big part of machine learning, I'd be like, you're crazy. Machine learning is about data from some source that you don't have any effect on. You're just getting data from other source and you're just trying to make a good prediction on it. You're not affecting the world. There's no competitive environment. There's no, the idea that somehow we're using machine learning, which is the original assumptions where you have data from an IED distribution that you do not affect. Now people knew, well, if you're going to use it for finance, maybe you're going to affect the prices of things in the future because you're buying. Okay, but let's just make an assumption that you're not going to do that. That was always sort of the model, that there's no effect on the environment. We're in this world now where no, you're definitely affecting the environment, and we're still going to use predictive algorithms to play games. And I just emphasize that because I think it's an interesting place that we've come to, and in some sense an important place because, of course, in any real world environment, you're engaging with something, you're making decisions, and the other parties in the system are also seeing your decisions and probably adapting to them. So this talk is going to be about kind of an abstract view of how you can think of particular optimization algorithms through the lens of game playing. And I have to say, one of my most favorite, I got excited by machine learning, honestly, through the lens of game theory. And I think you'll see that. So let me just give you a sense of what we're going to talk about here. I want to describe just the basics of online learning, online convex optimization, as sort of a counterpart to vanilla convex optimization. And we'll just discuss what is weighted regret in online convex optimization. There's this master protocol for solving min-max problems, for solving certain games, zero-sum games, called the master protocol. And we're going to use this as a way of solving basic convex optimization problems. Vanilla convex optimization, using this thing that you call the Fenchel game. You're going to convert any optimization problem, you can just convert it into a min-max problem through this Fenchel game idea, and I think it'll look familiar. And then what's going to happen here is this is going to be a MadLib recipe for making algorithms, for just producing vanilla standard convex optimization algorithms using this kind of master protocol in online learning. And I'll show you some examples of this. And this talk is really just going to give you a high level of this sort of idea. I think it's a really cool idea, and in some sense, I'm worried that I'm not going to impress many of you because I'm going to be showing you things you probably already know. But I want you to just try to appreciate the perspective where we can describe a lot of existing techniques in optimization using this sort of view, this protocol, Fenchel game protocol view. So let me dive in. Okay, in standard vanilla convex optimization, you're trying to minimize a fixed function f, and you typically do that by making queries to f or gradient of f or Hessian of f, etc. for a sequence of points. You pick, x1, x2, but then these are just things you're querying on. In the end, you output some x hat that's hopefully going to minimize, get close to argmin. We're going to have a small value on f relative to the minimizer. Okay, so that's the standard vanilla convex optimization perspective. You're just trying to find that x hat, which is almost a minimizer. Okay, the online learning view, or online convex optimization view, if we call it, you're actually looking for a sequence of points that minimize regret. Now, the key thing here is that the function that you're being measured against are changing. There's no fixed function. There's no fixed objective you're minimizing. You have this sequence of functions, L1, L2, L3, which are changing, and you're trying to do well against this adapting sequence of loss functions. And you can actually assume that these loss functions are chosen in an adversarial fashion. The cool thing here is that there's no stochasticity. These things you haven't seen yet, they're arriving online. You're choosing a sequence of points, x1. So it looks like optimization, just vanilla optimization, because you're still choosing a sequence of points, x1, x2, but you're being measured by different things on every round. And you're going to pay kind of the total loss along the way, but you're going to compare yourself, this total loss you paid along the way, to some best x. If you'd seen the data in advance, what x would you have chosen? You would have chosen this x star, and you would have paid the sum of the losses over time. Okay, so there's just two perspectives here. There's vanilla optimization, and there's online convex optimization. I can show you the protocol of online learning, online convex optimization. Again, usually you sort of assume you have a decision set Z. Maybe you know the number of rounds you're going to play this game T. And I'm going to do a weighted version. It's important that I have a weighted version here. You have these weights, they're positive, alpha 1, alpha 2, all the way up to alpha t. And maybe you know these in advance, it's fine. Maybe they're coming online, but you can assume that you know them in advance for now. And there's some online learning algorithm called OALG, online learning algorithm. So for every little t, you call your online learning algorithm to get a point zt. This is going to be inside of your set z. And then you receive both a weight and a loss function, LT. And we tend to assume these loss functions are convex, LT. And then you pay kind of the weighted cost of your decision. You pay LT of ZT. Okay, and that adds to your loss. And in the end of the day, you want to minimize this quantity. It's how much money you paid to play this game, or the weighted cost of your decisions, versus the weighted cost of the best in hindsight single decision. It's how much you paid total to play this game. You paid this much to play, but you could have paid this much to play if you had known these in advance and could have just minimized over z. So it's how much worse did you do than this best in hindsight point? And also sometimes we take the average regret, which would just be the regret over this. This is the total weight. This is the sum of the alphas. I'm just normalizing this by the total weight. Okay, so this is the weighted regret. Most of the time when you see regret, you don't see weights, but it's important for this framework. Yeah.
Are these loss functions again the adversary can choose them adaptively?
Can choose them adaptively if you want.
So, but in your regret definition, you're evaluating against the loss function that.
Yeah. Okay. So you're making a philosophical point. I'm going to repeat it because it's a good one. Philosophically, yes. I'm saying, the adversary can adapt to any. I'm saying, or the opponent, or the learner can adapt to any sequence of LTs, and the LTs can be adapting to your sequence too. So there could be some adapt. But in some sense, the fact that I'm comparing against a fixed z kind of says that maybe it's not really adaptive because the z that I compete against isn't fixed, and that's sort of true. I don't think it means this is an uninteresting objective. It just means that there is a sense in which it's not adaptive. Yeah.
I guess you're looking at fixed z in hindsight, but also the loss function, the LTs are fixed. You're looking at.
I'm sorry. What was that?
These LTs, the loss functions.
The loss functions, yeah.
They're also fixed. I mean, that if I played this fixed z, the adversary might have actually chosen a different sequence of loss functions.
Could have chosen a different sequence of loss functions.
Compared to policy or that.
But you're just.
Oh, are you saying that you could imagine a z that changes over time?
Well, both the LTs are. Are you saying the LTs could be adaptive to your z, right?
Yeah, the LT could depend on xt minus 1, or zt minus 1, zt minus 2. Yeah.
But here, when you're evaluating your regret, you're evaluating for the LT that was realized, not.
That's right. It's a very empirical process. And I'm seeing an empirical sequence of LTs. Maybe they're chosen stochastically. Blah, blah. When I ask myself how did I do in the end, it's on that observed sequence of LTs. Even if they were stochastic or whatever, I'm interested in how I did it on the observed sequence, which is different than some types like bandit algorithms. Sometimes you say, well, what's the expected best star? This is on the actual observed sequence, which is a choice. In my model.
So if I give you a different sequence of points, you'll have different sequence of L's.
Wait. If I get different sequence of L's are what you're taking as input, and you're outputting the ZTs on the way.
Okay, but L's are adapting, right?
Yeah, so maybe some adversary is choosing the L's because it's seeing that I'm my ZTs.
So I guess my question is, if I give you a different sequence of Z's,
Yep.
the first term in the regret will change.
Yeah.
And the second term in the regret will change as well.
If the L's were adapting to my Z's, yes, that's true.
Okay,
Yeah.
thank you.
Yeah. Maybe it's not good to think. No, for the whole framework that I'm going to set up, I actually need them to be adaptive. They are definitely adaptive, but that's okay, and it doesn't hurt the proofs or anything. Yeah.
Can those alpha coefficients be captured in loss function as well? What is the point of thinking about them separately?
Sorry, I'm thinking of what separately?
Can those alpha coefficients be also captured within the loss function?
You're absolutely right. Why am I incorporating? Why do I have these alphas? It does seem a little strange, and I think this is why no one ever presented weighted regret before, because it doesn't seem like it's useful. You could just call this the loss function, alpha t times LT. It does actually matter. And it matters because of the fact that I'm going to output weighted averages of my z's. It does somehow matter. I think you'll see where it's important to have weights. It's a good question. Okay, so what's the most basic online convex optimization algorithm? It's gradient descent. Of course it is. What else could it be? Well, it's online gradient descent, you could say. You just take xt plus 1 is just xt minus some parameter times the gradient of LT. Remember, this is a changing function, so it's at the point xt. This is like stochastic. This is stochastic gradient descent. I said these LTs aren't stochastic necessarily. They could be adversarially chosen, but it's okay. It feels like stochastic gradient descent. Just move your parameters over in the direction of the gradient of that current loss function on that current round.
So why not of the aggregate of the class function?
Oh, good. I mean, you could do that. I don't know if that's going to give you a good regret bound. I mean, this I know gives you a good regret bound. In some sense, the most basic proof. This basically was Zinkevich in like 2003, who showed that this algorithm has a root T regret bound. Hold your thought on that. You're going to see algorithms that look more like that, what you have in mind. So this is the basic algorithm that a lot of folks use, and there are other algorithms. I'm going to talk about that in a moment. But just if you're like looking for kind of like, oh, what's a classical algorithm? What do I know about it? This one right here. The key thing here is that the average regret is going to 0. There's no weights here. Just some of the weights are all 1. So this is just a standard average regret with uniform weights. But that 1 over t, notice that this is going to 0, and that's a key point, that there are algorithms that have vanishing regret over time. Okay, let me tell you about something that has always bothered me. And it's bothered me for a particular reason. I've done work in grad school. A lot of the work that I've done over the years is like showing that that algorithm and that algorithm, they're the same algorithm actually. In fact, everything is really just one algorithm. Everything is just mirror descent in some form or another. There's really no other algorithm. For online learning, there's like no other algorithm. There is one algorithm. And I'm gonna lie to you and tell you that there's actually more than one algorithm, and I'll have an example. But basically, there's just one algorithm, and this has frustrated me, because you look at like vanilla convex optimization, and you have all these fancy algorithms, and they seem to be having like different flavors to them. You have all these like versions of Frank-Wolfe. You have gradient descent, but then you can also add momentum. You have heavy ball, and all of a sudden you have this other algorithm, which isn't quite gradient descent. You have Nesterov acceleration, which is like somehow a modified heavy ball, but isn't quite that. And you have these various versions of Nesterov, and I was always confused. Why is online learning so much simpler in the algorithms than vanilla? It's like a harder problem. You have the changing function. Like, why shouldn't the algorithms be more interesting on the harder problem? Vanilla convex optimization, I just never understood why are those algorithms so much more interesting than our algorithms? Why are all of our online learning algorithms sort of the same? I'll explain what I mean by that in a little bit. And it turns out, I think part of the talk is going to show that actually they all kind of fit into an interesting category. And they actually can be described through the lens of online learning. And this is maybe the biggest point I want to make. That a lot of these techniques, you can view them as actually combining two online learning algorithms. So just hold off on that, and we'll get to that. Should I stop and take questions before I move on? I have to stop at 5:15, right? Yeah. Okay. So where we're going is that a large number of these classical first-order optimization algorithms are in fact can be viewed as dynamics of a two-player zero-sum game being played by two no-regret learning algorithms, two online convex optimization algorithms, just combined in the appropriate way. There's some sequential zero-sum game that is being solved, and it's just being solved by two particular players that have made particular choices of the type of online learning strategy that they're using. So I should emphasize that the big player here is my student Jun-Kun Wong. I couldn't find a good photograph of him, but he's now a postdoc at Yale, on the job market soon if anyone's looking to hire. And also with help from my student Kevin Lay and Kfir Levy, who's Kfir is on the journal submission that we just made. Okay, so this is the rest of the talk. I'm just going to kind of show you this idea. But I have to tell you the protocol. What's this protocol? I said two game, I said two players. So I'm now gonna like step away from loss functions. There's these changing loss functions. Now there's a single payoff function, two input payoff function, G. G is convex in X and concave in Y. So it's a convex concave payoff function or loss function, whatever. It's just it takes two inputs. We're still gonna have these weights, alpha 1 through alpha t. And there's now two algorithms, two online convex optimization algorithms, no regret, regret minimizing algorithms, OAlg-Y, OAlg-X, that are going to be implemented here. Now, online learning algorithms require a sequence of loss functions to take as input before the output points X and Y. What are those loss functions? Okay, so on round T, OAlg-Y, this is the Y player's online convex optimization algorithm, online learning algorithm, outputs parameters YT. OAlg-X, I guess the way I've done this is sort of funny. I've like done the order a little bit funky. So first YT is chosen. So there's essentially a question of who goes first. Let's now assume that YT goes first. The Y player goes first. YT is output from the online learning algorithm. Once YT is chosen, we can now fill in this game payoff, this G. We can fill in the YT and leave the X value blank. We now have a loss function for the X player, HT. So HT is now being fed into the online learning algorithm for X. And now the online learning algorithm for X outputs XT. And now we can fill in the XT for this game payoff function and feed this thing into the online learning algorithm for Y. So let me emphasize here. We can have a loss function for the Y player and for the X player, but those are generated after the X player chooses its action and the Y player chooses its action, right? Because you can now just fill in what's going into this game payoff function. Is this clear? This is like a really important part of the talk. You should really understand this. In a two-player zero-sum game where you have this payoff function G, you can kind of fill in. If you fill in the Y player's value, you have a loss function for the X player, and if you fill in the X player's value, you have like a gain function for the Y player.
So you, I assume you use a Boolean descent, right? So
Well, actually,
on this generally, you abstract and return that XT, YT is hiding there.
we're going to use a whole bunch of different algorithms, but gradient descent is one of them. Yeah.
Okay.
So this is a protocol. This is a protocol. I'm just setting up a protocol. This is like I have choices I have to make still, but I can imagine this protocol. Yeah.
So, just trying to make sure I understand. Why KOY is making an irrevocable decision in that first instance?
Yes. Yep.
And then X, using that information, is coming up with their own loss function conditional on that kind of
Yep.
information to make their decision. Then you're updating the loss function for Y, and then Y is charged for the updated loss
Yeah.
function.
So I'm looking at this now, by the way, and I should emphasize there is a version of this protocol where this line is put up here, where they both simultaneously commit to their parameters, and then they simultaneously receive loss functions. I've actually done it the smart way in that I've like, now X actually has the ability to look at Y's action and then use that in the Or it could say, I'm going to wait, I'm not going to use it on this round, I'll use it on the next round. So I mean, in some sense, this is more general, because, this thing could like ignore the most recent input or something. But it's actually an important point, and there are certain algorithms that I'm going to talk about later where it actually is very important that we did it in this order. And in fact, the order is going to be it's going to matter. Which player goes first is going to be important, and or are they going to peek at what the other player did? So hold that thought, basically.
But this is the more symmetric algorithm because somehow on sequential terms, each
That's
one
right.
is updating based on-
You'd expect that you'd want to, if they were available, you'd want to use the data coming from this other player. Yeah, good question. Very good question. Yeah.
Does it matter who goes first, and also does it matter?
It does matter who goes first, and in fact, I'm going to be using different versions of this.
And does it also matter? The minus sign here is in.
Why is the minus sign here? The minus sign here is because the X player is it convex concave? Did I mess it? I may have messed up the order here. It's convex. It's convex in X. I think I messed this up. It should be a negative sign should be down here actually. And this is I'm off by a bit. So it's like I want this to be convex. This should be convex and this should be convex. So I think it should have been negative down here to ensure that. Oops. Okay, good. By the way, I'll just emphasize, we'll talk about this later. The output of this algorithm is the weighted average of the X's and the Y's chosen along the way. This is going to be important, but hold off on this sort of, why is this here? This has nothing to do with playing the game. But somehow this is important that we're going to use the weighted average of these x's and y's. Okay, so I want to emphasize that what we have actually, this protocol, in some sense, lets us prove the MinMax theorem. A generalized MinMax theorem. We're going to prove that if you inf over x and sup over y for this g of x, y, it doesn't matter which way you go, whether you inf first or sup first. And the proof is actually, what I love about this proof is that it looks very complicated, but there's actually nothing in this proof. I'm literally going to, the only inequality that's interesting is basically Jensen's inequality. I'm not going to apply anything other than Jensen to get this proof. So all you do is you analyze the weighted average of the losses of the x and y player. Well, this is, I guess, the losses for the x player and the gains for the y player. Okay, so I have this payoff function right here, g. I'm taking the weighted average of that thing. So because I've defined the loss function for the y player LT just to be exactly g of x y t, I can just, this is just, I think this minus sign is maybe wrong. Anyway, I'm sorry about that, but this is just a definition, right? And now I use a definition. What is regret? What is the average regret here? The average regret is the difference between how much you paid to play the game versus how much you could have paid if you'd sort of picked the best y in hindsight. So, I mean, regret is just the definition of the difference between these two things. So this inequality holds essentially by definition. And I guess, okay, this is going to replace this with the average regret. That's what this is average regret. And then because I have a sup over y of a weighted average of these like payoff functions, I can put, this is convex in x, right? So I can pass this whole thing through. This thing can just pass through to become, okay, now it's g of the weighted average of the x's. That's the only interesting part of this proof is Jensen. Only interesting part. Now I have sup over this weighted average, g of this weighted average x, comma y. But this particular choice, this is a weighted average of points in a convex set, so it is also a point in that convex set. We'll call it x bar. That is not, that is definitely not as bad as the inf over x. I'm going to replace this x bar with the inf over x of the same thing. Okay, the only thing I have left over here is a regret term. The regret term is kind of like this. I'm pushing under the rug the fact that, like, well, I wasn't paying this. Sorry, I wasn't paying this. I was actually paying this, but the difference between these two things is going to go to 0. So, like, let's just shove that in the rug and call that regret. Okay. So I have this quantity here, which is the average price paid by one of these players, and I can just analyze now the other side of this thing. Let's go to the other side. The other side is exactly the same proof. I don't even have to show you the same proof because the proof is the same. Go through the same exact process with the other player. Both players are minimizing regret. The other player that's minimizing regret is going to do the exact same sequence of steps, blah, 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 blah. But it's going to find that they're going to end up with a sup and an inf here. Plus a regret for the x player. They're going to have an additive regret term over here. If you just put the two statements together, the two sequences of arguments together, you get like inf sup g is also equal to sup inf g with these two terms that are basically sandwiching these two, the min-max and the max-min. But these two things are going to 0. That's the assumption, at least, that I have an algorithm that can guarantee sublinear regret or vanishing regret. And this gives me a proof of the min-max theorem. But what's more important about this is not just a proof of the min-max theorem. This is a construction for the min-max theorem. I actually want to find good points x and y. Which ones do I use? I'm going to use these x bar and y bars. If you actually just snake through this proof, you will see that this y bar here, and on the previous slide, this is the one on the okay. This x bar that I got and this y bar basically are they are approximate min-max points. They are approximate min-max points, and more importantly, how approximate are they? How much are they off in the approximation? They're off by exactly the average regret of the x player plus the average regret of the y player. So somehow magically, I had these two algorithms. They were competing against each other, choosing points xt, yt, xu, right? And in the end, I just like ran this protocol, took all the points, took weighted averages of them, and I'm guaranteed that the weighted average of these x's and y's are almost min-max points, and they're just off by this much. So if you can tell me the regret of both of the players, on average, this should be a bar, these are average regrets, then I have now produced an approximate min-max point. So I've actually solved this equilibrium approximately using these online learning strategies. Okay, this is a key point. This is in some sense like the most important point. I'm kind of like taking this protocol, having these two players compete against each other, watching what they do, and then outputting the average actions that they took. Let me just tell you, the question is what, so the only thing I didn't tell you that was maybe very important yet is, where did this G come from? What G should I use? I mean, actually I can use any G, this works for any G, but I'm going to propose a particular choice of G. How about this thing we call it the differential game. Take any function f, you want to minimize some function f, turn that f into a two-player game. I mean, it seems weird. You have a one-input function, turn it into a two-input function, which is defined in terms of the differential conjugate of f. This is simple. I mean, you've probably seen this objective before. X dot y minus f star of y. This game, I mean, in some sense, one of the key things that we realized early on in this research project is that this is like the fundamental game. This is the kind of key thing you should be analyzing. And people who know duality or probably won't be surprised by that this is sort of the right quantity. The key thing is that if you have found, let's say x hat y hat is like an epsilon approximate equilibrium of the game G, this particular game G, then we'll just throw away the y hat. That x hat right there is going to be an epsilon approximate solution to the minimization problem. That's why solving the game, approximately finding an approximate equilibrium to the game, actually implies that I have an approximate solution to the minimization problem. It seems very convoluted, by the way. You probably are thinking like, well, this is much simpler than what you just showed me. This whole nonsense is way more complicated. Yeah, but this last protocol lets me build algorithms. Lets me construct algorithms. So if you're willing to let me take the simple minimization problem and turn it into a complicated solving a game with two players, I can now build algorithms. You have a question? Any questions about this before I move on?
This is convex. So
What's that?
this is convex.
So f star is convex, but now it's negative, so it's concave in y, and it's linear in x. So actually, yeah.
It's F originally.
Oh, sorry. Yes. Yeah, so let's assume that f is convex. This whole thing assumes f is convex. Yeah. Yeah.
How is this different from just a reformulation of the primal dual algorithms?
Well, I would say this is another way of thinking about the primal dual. It is a primal dual method for sure. But the point here is that there's a lot of flexibility in what you're doing in primal and what you're doing in dual. And you really want to combine those in interesting ways. And I think you'll see that the strategies you choose for primal and dual are going to be interesting. And my point is that you pick any strategy for the X player and any strategy for the Y player. If you're minimizing regret on both sides, you have an algorithm that will solve this problem right here.
Is this just a different name for primal dual?
Sure. So I should say, if you came from kind of the online learning world, computing equilibria and zero-sum games was something that people were interested in separately from optimization. And then we realized, if we just apply that to this primal dual problem, in applying the right types of algorithms, you get kind of, neat things from that. Any, yeah.
So there's a sort of a slight asymmetry here, but I think you're going to fix it. You should throw away y, keep x. X is an approximate optimizer. Y is... I
think y is going to end up being, it should converge to zero vector. I think y converges to the gradient at the minimizer. It converges to the gradient at the minimizer. That's what I should say. But you don't need that for the problem at hand. So yeah, the x is the thing that kind of comes out of this procedure. Okay. So anyway, the point I was trying to make initially is that this kind of gives you like a MadLib. You guys know what MadLibs are? Who knows what MadLibs are? Maybe some of the international students don't know what MadLibs are. It's like they have there's a book, have a story it's telling, and it's like they have fill in the blanks. You can fill in the blanks and make up your own silly story. It's for kids. But this gives you a MadLib. You can now choose whatever you want for the alphas, whatever you want for the algorithm y, and whatever you want for the online learning algorithm for x. And also the order of the players is another thing you get to choose. So the rest of the talk, I'm just going to show you some examples of what happens if you fill in some of the blanks here. But before I do that, I think I need to tell you about some of the kind of classical online convex optimization algorithms. So this is what I just said. We've titled this thing "Fential Game No Regret Dynamics," and what it does is it lets you basically build an optimization algorithm by making two particular choices of online learning strategy, no regret learning strategy. So what I'm going to do now, I'll do in a little bit, is show you two interpretations of every algorithm. One is sort of the classical iterative procedure, and the other one is going to be kind of the perspective as a pair of no regret algorithms. But I'll get to this in a second. First, I need to give you the menu. What's on the menu here? Okay, so classical online convex optimization strategies. Follow the leader. Follow the leader is like one of the simplest online learning algorithms. You have a sequence of loss functions L1 through L, let's say T-1 you've seen so far, or you've weighted loss functions. Just play the point that is minimal in hindsight. The point that's best in hindsight so far. This goes up to T-1. So you're choosing on around ZT. You could imagine minimizing up to around T-1. You could also imagine cheating and getting one extra data point. Like you shouldn't. This is the case when you somehow, if you get to see the loss function in the current round, I can actually just go up to T. This is getting to your point earlier about like, well, what if you're the second player? You're going to get one more data point before you choose. Yeah, so you could actually do this up to T in some cases. So whenever I have an algorithm that gets to cheat, I put a plus. It's getting a little. It's like it gets to be the second player. If you're kind of second in the protocol, you get to kind of do something at round TL. So you get an extra data point. Okay, very simple online algorithm. And by the way, I should have included it, but there are bounds for this algorithm, regret bounds. You actually need to ensure that these loss functions are shown in convex. You don't really get regret bounds unless the loss functions are shown in convex, or they have to have other properties. But strong convexity will guarantee a vanishing regret. Okay, follow the regularized leader. These are kind of terms that the online learning community has come up with over the years. You can imagine just simply adding a regularization term to this optimization in every round. And usually, you choose this as like 2 norms squared or something like that, or entropy or whatever. Now you're going to solve this regularized minimization problem on every round. Or again, you can also imagine a version that goes up to T versus T-1. This is this is a sort of cheating algorithm that gets peaking at one more round, but let's imagine that you could peak at one more round. Okay, so I'll add one more. So up until now, this was, I was making this point. All these algorithms are basically the same, and up till now, you'll notice they kind of are all the same. I mean, there's nothing. I mean, all I'm doing is solving an optimization problem in every round. There's one extra exception to that. There's this new class of algorithms that I have to say was one of the key people was Karthik Sridharan. Is Karthik here on the call? I can see his name on there.
Yeah, I'm here.
Hi, Karthik. Is the idea of using what's called optimism. I guess this goes back to a paper of Chang et al. In 2012 in some cult paper. They realized that if you can solve this, you can just minimize over the data you've seen so far. You have kind of like these loss functions you've seen so far. Do the best on the data you've seen so far, but add to this objective an extra piece, an extra thing to this objective. What do you add? Let's assume you had a really good guess over what the loss function was going to be today. Let's call it MT. MT was a loss function that's going to happen today. I'm just guessing. I don't know if this is right. Just add that into the objective function, MT. Now, what do you think would be, if I was to say, what would be a good choice of a guess for the loss function today? Any ideas? Karthik, do you know? What would be a good guess for the loss function today?
The loss function yesterday.
The loss function yesterday, which is actually the only case that I've ever seen used, is that you basically insert the loss function in yesterday. So typically, every time this is really ever used, again, this is LT-1. MT is equal to LT-1. Okay? So this idea of optimism, you basically think, I know what's happening today because it's the same thing happened yesterday. I'm just going to guess it was the same thing happened yesterday. Okay, that's fine. And again, you can also imagine a regularized version of this. This is, and in some sense, I'm calling this the master algorithm because actually every other algorithm I've just shown you is a special case of this. That's what I'm saying. There's really only one algorithm. This is it. This is the master. Everything else is a special case. Okay, so let's talk about that optimism idea. There was this, the idea of optimism was kind of, people were thinking about this like in the early 2010, the 20 teens, people were starting to realize there was something interesting about kind of replicating the previous loss. Something was cool about that it wasn't clear before. There was a paper by Daskalakis et al. That sort of was decoupling Nesterov, and it had this sort of extra thing that was maybe interpreted as optimism. Cheng et al. Was like the first to really write down that if you think that the loss functions aren't changing very quickly, then you can take advantage of that using this essentially optimistic algorithm. And then it was Rocklin and Sridharan who observed, I was very surprised when I saw this, that you can actually use this technique to solve zero-sum games. Like simple zero-sum matrix games can be solved faster if one of the players, or I think they actually had both of the players, using an optimistic online learning algorithm. And it was like surprising. It's 1 over root t rate. I assume it was best possible for solving games, but they got it down to 1 over t, and that was a real surprise. And it turns out, and I think this has kind of been one of the key points that we've been realizing in the sequence of research papers. This optimistic idea is the key secret sauce to getting acceleration. Every time that we found an accelerated algorithm, something that went from like a 1 over t to 1 over t squared, it was always because you're adding this optimistic thing. And if you kind of look at that, and you think about what's going on here, it shouldn't be surprising. If this was like, if you were doing some kind of this kind of, you can view this as like a gradient. This can be viewed as almost like a gradient descent. You'll notice that like you're kind of duplicating LT minus 1 twice here. But then you have to sort of correct it in the next round. And it ends up being you like add the gradient twice in the current round and then subtract in the previous round. Which is sort of like what you see when you like look at acceleration algorithms. They always have this like 2 gradient on the current round, minus gradient in the last round. That's actually what's going on here. And so basically the like secret sauce of this optimism was sort of the secret sauce to get accelerated algorithms. And you're going to see examples of that going forward. So let me just throw in a couple more algorithms, even though I said that they're basically all part of the same family. There's one that isn't really part of the same family. It's best response. Best response is like a trivial algorithm. If you see the loss function on the current day, LT, just best respond to it. Pick the argmin against that. This is like not even a real algorithm. If you tell me the loss function today, I'm just going to pick the best thing you really could do is just pick the minimizer on that particular day. So this is like again, I put a plus here because it's sort of a cheating algorithm. It's looking at the loss in the current round. Okay, best response. I do need that one. That one doesn't really fit in the same family. The kind of mirror descent family is maybe the last category I'll mention. So you have the standard mirror descent type algorithm where you kind of, this is a Bregman divergence term. You're doing a prox update or whatever from the last ZT minus 1 to get ZT where you're adding in the loss function on the current date. This is probably very familiar to anyone who's done optimization. And it turns out that this is like very much like follow the regularized leader. If you write it correctly and you have the kind of the right setup. This is again very similar to FTRL under certain conditions. And of course you can imagine an optimistic variant of this. So the optimistic variant of this is, well, you sort of do a half step. You kind of compute ZT, but it was computed from like the half step on the previous round. But then you did this kind of gradient update. To get the half step, you sort of have to do this one additional gradient update, one additional mirror descent update. And I'm sure folks have seen something like this before if you've looked at kind of acceleration type algorithms. Okay, I've given, yeah.
Yeah, so I was just going to ask about the optimism. Like, the best guess you can guess about today is just do yesterday. Like, what if you did the day before? Like, do you get the same results?
I don't know. That's a good question. I haven't thought about that. Yeah, I guess we haven't done a lot of, oh, I'm out of time. We haven't done a lot of, I haven't thought that far on that, but it does seem that if you kind of look at the bounds, you really want the difference of what you did today, what happens today and what happened yesterday. That comes up in the, how off your guess was is very important. So I don't have a quick answer to your question. I'm realizing I'm out of time, and so I'm going to have to rush through, but I just want to show you kind of using this framework and using the online learning algorithms I've shown you so far. Let me just give you a couple of examples of how you can use the protocol and the framework to kind of build certain algorithms. Okay, classic algorithm, vanilla gradient descent with iterative averaging. Your eta is chosen this way. Your WT is updated. This is again standard iterative view of iterative average gradient descent. You do a standard gradient update from your previous point, and then you kind of maintain an average of that, and then you output that. Okay, what is the master protocol version of this? Master protocol is you have the standard differential game. The X player uses online mirror descent, and the Y player is using best response. This is actually a way to interpret what vanilla gradient descent is. It's online mirror descent versus best response. Okay, how about Frank-Wolfe? The standard Frank-Wolfe is every day you update, you pick you've computed the gradient on the previous round, and you to do a linear minimization from that gradient over the feasible set. Okay, you assume you have some oracle that can answer this question, and you do kind of a weighted average with your previous point. What is that? Well, that's follow the leader for the Y player and best response for the X player. Right? It's just follow the leader versus a best response. I can keep going. I didn't want to get into details and I don't have time, but this is how simple the proof is. The proof is simply just writing down what are the regret bounds for the two players and adding them up and doing some simple analysis. And you get these like 1/t rates, the standard 1/t rate for Frank-Wolfe. The key thing is that we offloaded all the work to proving the regret bounds. Once you have the regret bounds, you get convergence rates to the optimization algorithms very easily. I want to get through a couple more. Heavy ball algorithm, you do this kind of like gradient update, but then you have this like momentum term as well. VT is like the difference between the last two iterates, and that gets added onto your objective. What is that in my world? Follow the leader versus online mirror descent for the X player. And by the way, proving this equivalence does take some work. So I'm skipping the details here, but I'm just telling you there is a way to interpret this algorithm as this. Yeah.
When you say equivalent, what exactly do you mean? You mean that
the iterates that are produced are identical. Identical. Yeah. That requires an inductive argument to show. But more importantly, and one thing I'm not showing is that like the convergence rates come by just looking at the regret bounds for these two algorithms. You add the regret bounds up, and that's how you get the convergence rate. Okay, let me just get through a couple more, and I know that I'm over time, so I'll just take a couple questions. Nesterov's accelerated gradient descent, the one memory method. You may have seen it written this way. You kind of have a ZT that gets updated from the previous WT plus some VT minus 1. VT is chosen as some like mirror descent type thing, and then you kind of average the WT and the VT together. That is optimistic follow the leader versus online mirror descent. That is a way you can interpret what is happening over here. You get the identical algorithm. Similarly, if you want to do this for the infinite memory version, there's this infinite memory version of Nesterov where you kind of maintain all of the gradients so far, and then you solve like a minimization over this regularized objective. That's the infinite memory version. And the same thing is, it's optimistic follow leader against this FTRL plus algorithm that gets to peak. So it's kind of cool. Maybe I'll just mention that there are some new algorithms we came up with. You have a gauge Frank-Wolfe, which has a faster rate. You get a 1/t² algorithm. And we came up with this new thing that we're still trying to understand, which feels like an acceleration algorithm. You kind of have two updates going on here. But it comes from just applying optimistic mirror descent with the follow the leader algorithm for the Y player. And somehow we got this 1/t² rate. And I'm honestly still trying to understand this particular example. Since I'm so over time though, why don't I just say that the conclusions here, we notice that if you take an optimization problem, turn it into a MinMax problem, allow both the min and the max players just to choose their own online convolutional optimization strategy, you can get a straightforward guarantee on convergence rate, and you end up getting a kind of a cool algorithm. We were able to show that kind of there are many well-known algorithms that can be described in this framework, and you also get a number of new novel algorithms that we were honestly surprised to find. Let me stop there and say thank you. And my sincere apologies for going over time.
I guess I've already told you his email address. If you had questions, you'd be surprised. You actually do get responses. But since it was 1.5 talks, I guess maybe you can take a few questions. Feel free to leave if you're late. Or
you showed a sort of, in some sense, here's a traditional algorithm, here's the way to put it into your framework. Is that an algorithmic process or is that a inspiration process?
Well, I'm going to answer the question in a different way, which may not be what you asked. But what we first did is that we realized, oh, Frank-Wolfe can be described in this like zero-sum game framework. And then, of course, we just said, oh, it's what one player is playing follow the leader and the other player is playing best response. And I just said, what if we replace it with gradient descent versus best response? And we just looked at the iterates. That's heavy ball right there. And then we said, oh, well, what if we replace? We just kept. This is the process. We sort of kept realizing, like, oh, what if we tinker with this framework a little bit? What happens? We get this new algorithm. Oh, no, that's Nesterov acceleration. Oh, okay. Well, we haven't got. And then eventually we found novel algorithms out that hadn't been worked out before, or we don't think had been worked out previously. You know, which required certain assumptions, whatever. But so I don't know. I mean, I guess what I'm trying to sell here is that. Maybe there's some other ways this can be used. I mean, we were sort of rediscovering a lot of old stuff, but rediscovering it, I think, in a neat way. And the fact that this framework modularizes everything and lets you kind of prove convergence with such a simple, as long as you have regret bounds for online learning algorithms, you immediately get convergence rates for these optimization algorithms. That seems to be the real value of this. Yeah, did that answer your question?
It did.
Okay.
Maybe as a follow-up, like a lot of these algorithms were discovered as the MinMax optimal under a certain class of functions. Do you think there's any principled way in which, if I restrict the class of functions, you can automatically tell me what are the...
That's a great question. I don't have a good answer to it. I don't know. Yeah, I mean, whether these were optimal approaches, I don't know. I mean, again, I think I was already surprised that Optimism somehow lets you solve zero-sum games faster. Maybe you can. How do we know that's as far as you can go? Well, we have lower bounds in some cases, but yeah, it's a good question. It's a good question.
I'm just curious, like, is there any connection in the low dimension setting where the optimal algorithms are like cutting place and more like non-gradient based something?
Yeah, no, it's a good question, and that would be, maybe we should work on that. That sounds like a great problem. I don't know.
Another quick question. So in the first line of your game theoretic connection, you use the sequential duality and the MinMax formulation. And somewhere like over there, you directly went to global property, right? Like the gradient descent algorithms work even if the iterates that you produce are like somehow locally convex and like along the path, it looks convexity. So is there like a...
What do you mean by local in this case?
So like all you need for like convergence of SGD or something is the path that you observe is like convex with respect to a minima.
Well, convex is a global property though, so I don't know.
Yeah, but like only on the 2 points that you care about for linearization.
Oh, I see, like the minimum and the point you were at, is that what you're saying?
Yeah.
Uh-huh.
And
you're basically asking, can we generalize this to non-convex settings? Yeah, no, okay, it's interesting. I don't know, there's so many places where we use convexity here. We use convexity to get the regret bounds.
Yeah.
We use convexity to define the differential game, in some sense, because you need that the dual of the dual is the original function.
Yeah.
So I mean, there's so many places that we're embedding convexity that I don't know if we could like peel away those assumptions. But it's a good question. But I've always been scared to try this for the non-convex because like everything's going to break. So many places that we're using convexity.
I have a question.
Sure.
One thought is, so Aisha Wilson at MIT has this approach of using like dynamical systems to study the performance kind of optimization algorithms. And I'm wondering if you could extend your approach using this MinMax kind of formulations to then thinking about maybe a differential games kind of formulation.
Yeah, so you said Aisha Wilson has some work on differential, viewing optimization through like a differential equation, solving a differential equation. I will tell you that Aisha Wilson did that work with Andre Wibisono and Mike Jordan. And I had that exact same thought, which is why I hired Andre Wibisono as a postdoc for 2 years. And we thought about this for 2 years and we never didn't solve it. So I think the answer to the question is no. But I have talked a lot about that connection. So it was good that you had that intuition. But I spent a lot of money on that question. That was like $150,000 of salary for that to not get an answer to that question. So.
We're still recording, by the way.
Oh, I'm still recording.
You gotta give the money to Asia.
Any other questions? All right, let's thank Jake again.
Thanks for having me, guys. My first talk in 2 years. Thanks a lot, folks. Yeah, this is a lot of fun.